this picture in front of you right now is one of our numerical relativity simulations. It's kind of mandatory that we have some pretty pictures. This one was of a relatively recent event, GW 1905-21. So that means it happened on the 19th of May, 2021. And it's a tricky event because of its masses being very large, which meant there wasn't very many cycles detected in the ground-based detectors band, LIGO and Virgo. And this is a snapshot of the gravitational wave emission coming off. Of course, the star field, if you can see it, I don't know how good your projector is, the star field is fake, but the waveform is what it looks like as these two black holes coalesce. And so I'm just gonna talk a little bit about what we've been doing so far in this current era of gravitational wave detection and where we might go. So, assuming I can, there we go. I think for me personally, the excitement is the concept of gravitational physics being driven by data now, and it's just begun, right? It's barely 5-6 years old, where we've been changing how we see the universe now, also using strong field gravity. And I love that idea. And I think the future prospects of both ground and space are huge, and it's really going to change the way, I mean, we're going to see new astrophysics, and we're also going to see new fundamental physics. And I think the whole point of this talk is that future prospect places some demands on us, the numerical relativity community, and other theoretical gravity group communities, the people who predict and interpret the waveforms, because of the increase in accuracy and the increase of sensitivity of these detectors adds new demands on us. I also think it's an opportunity to use innovative data science and computing, although that is not something that I do personally well. I am very excited as I see all the new people coming to numerical relativity and some of the old familiar friends tackling new ways that we can do computing and machine learning, et cetera. So this little movie, it's kind of dark, so it might be hard for you to see, is the full simulation result from the snapshot that was on the first slide, just to show that beautiful waveform that we all know and love coming through. So I often show this slide when we're not talking to a group like us. I think most of us understand what the science drivers are of these gravitational wave detectors, but it's fun just to think about the sheer amount of stuff we are learning, have learned, and will learn. Is, Einstein's theory the theory of gravity? It certainly is acting like it is right now, but we have to remember we're just at the beginning of our probing the strong field regime. And although maybe this gravitational waves may not at the end of the day reveal any flaws in the theory of gravity or the general theory from Einstein, we can still hope and work hard to study it. Obviously, we see black holes at all mass scales, or we will if they exist at all these mass scales, and that's super exciting for both physicists and astronomers. You've heard again and again over the last 2 days about neutron stars and all the amazing things we can learn about these engines of the universe, gamma ray bursts, et cetera. And as we look towards space-based gravitational wave detectors, we start to open up to the formation of these supermassive black holes, and how those galaxies formed, the probe of the early universe, and even measuring gravity near the black hole as another black hole or star falls into it. So there's just a huge discovery potential ahead of us. And I think we're lucky to be part of it in this moment in time. Some of you know how boring it was. Well, I shouldn't say boring. But back when I was getting my PhD, it was a different landscape where it wasn't as fun to give talks because all I was doing was work on finite differencing stencils. But now I think it's an incredible opportunity. So this is just for fun. You've seen them already, but because I'm going to talk about the future, I thought I'd put today's landscape up there for us. We obviously know and love the two LIGO detectors and the Virgo detector in Europe. And of course, I wanted to show this plot because I think this Kagra illustration is quite lovely. Kagra is already part of the LIGO Virgo Kagra collaboration now. So Kagra is there. And this is an artist illustration of Kagra since it's underground, which is of course the detector in Japan. So hopefully when the next light happens, the fourth observing run of LIGO, Kagra will join and we'll start to have all these detectors looking at our events. And that's just a picture of the first event for fun. though you've probably seen it ad nauseum. So the theoretical landscape, when we look at the strong field regime of gravity, and I'll apologize if you guys have already talked about this since I've been distracted this week, but we are looking at post-Newtonian theory, perturbation theory, and numerical relativity. And we're really focusing this week a lot on numerical relativity, but when you think about it, you know, when you can get away with something else, if you don't need the full theory, you want to do so. So we have post-Newtonian when the speeds of the compact objects are not so strong, and perturbation theory when you can ignore the cell force of the smaller objects. You can act like a perturbation on a black hole background. And of course, numerical relativity, we don't assume anything and go full GR. So this plot, courtesy of Martin, there used to be an older one that Satya and Alessandra had, and they cleaned it up. This particular plot is a cartoon. It's meant to represent, I think, meant to represent the gaps in our knowledge from these different theories where we don't all overlap. It's not perfect, obviously. So this is a plot of compactness on the vertical axis and mass ratio on the horizontal axis. Numerical relativity down there in the lower left corner where we have the strongest field, where the speed is close to the speed of light and where we cannot ignore the fact that there's extent to these masses. And of course, we have the post-Newtonian theory above and the gravitational force over where, gravitational self force, where you're in the extreme mass ratio limit. And if we look at here where we have no thing touching, in that mass ratio limit that Carlos just talked about a little bit, you can see where we could have some concerns that we're not prepared with any one theory to detect an event. Hopefully you'd see it anyway, but you might not be able to interpret it to the quality we've come to expect. So that's where anyone sitting out there, there's a lot of work starting in this area, but we certainly haven't solved it. So what we actually do, so I'm trying to connect to the gravitational wave data analysis community with this talk a little more firmly. And so I feel like I have to do a quick mention of what does it mean when we say we're going to work with a bunch of waveforms and these templates. And what I mean is that the best way, if you have knowledge of the signal, like we do from any of these theoretical pursuits of the binary black hole problem, then it's best to go ahead and use that theoretical knowledge in the form of that waveform to try to detect and then interpret the signal. But of course, it's a game of you have an event and you have to decide, you have to find that correct template or waveform to match against the signal. So you take all of them in your bank, and the upper plot of these single red dots is what you could imagine a numerical relativity person providing, of a bunch of spin versus mass ratio where we do discrete points. And then you can imagine to the right that you've got a model of the waveforms where now you have a smooth transition between all those spin and mass ratios. And then you do some kind of correlation, which is a match filter, to find the best fit template. And when you do that and you find it, then we use that template and measure its parameters, et cetera. So numerical relativity has a role to play there because we're obviously providing that prediction of what the waveform looks like. And that's not the only thing numerical relativity is doing to contribute and guide gravitational wave astronomy. A lot is happening. I picked out a few of the most obvious things. The two plots above are from building model waveforms. So we do directly compare to the gravitational wave data numerical relativity waveforms. So you will find there was one paper from the very first event where we directly compared it for the first search, but mostly you see it in long authored papers. Actually, some people in the room and who have been giving talks are part of this effort, where we go ahead and take an event like GW 1905-21 that's a little bit unusual, and we compare it with the numerical relativity waveforms we have. Sometimes we run new simulations to see, is there missing physics in this? Is there something the models haven't gotten a hold of? Is there anything new we need to add to the story? So, that is something we do. And so that comes from individual groups contributing and also all the public catalogs that people have provided. But also people use, obviously the biggest thing people do is use the model waveform. So I'm thinking of the Phenom series and the EOBNR series, which are the two big model waveform series that are used. There are surrogate models, there are other things. So this is not exhaustive, but I just grabbed a couple papers, early papers from those two big phenomenological and EOB models. The one on the left, the plot on the left is from EOBNR from that 2007 Bonanno paper, and the plot on the right is from Ajit's 2007. So you have this way of using the information from post-Newtonian and numerical relativity and maybe even perturbation theory to create these models of the full waveform. And you get, for that, you get this nice, smooth understanding of how the waveforms vary with the physical parameters and hopefully speed. Not all these models are fast, but you want to be able to search over a large template bank quickly and produce a template bank quickly. One of the things that I really find intriguing when I first realized it is that I love the testing GR efforts that are happening, because I'm excited by the possibility that Einstein could be wrong, but that the original papers, the first papers that came out, they were really using the fits that the RIT group and Luciano Rizzolo's groups had provided, where you figure out the final mass and the spin of the black hole based on the numerical relativity simulations. So there's several fits that have been created. I think the RIT's groups are the most sophisticated now, where you look at, they basically fit these formulas. And so you provide the initial parameters of a system and out pops the final mass and black hole. And those types of fits are being used to look for consistency of the gravitational wave data with general relativity. Now, I'm not going to talk about matter, but I think we've heard a lot of talk, so hopefully I can get away with this. To see how exciting the possibility is and what's already happened with neutron stars and all the other neutron star black holes, binary neutron stars, you just have to look at almost every talk in this conference to see what's happening. There's a lot of, maybe I think this is going to be, the first binary neutron star was absolutely beautiful, as we all know, and we learned a lot. So it opened up a tremendous hope for the future. And I was listening to a talk this morning in a different conference, sorry, the Dawn conference, where they were talking about actually having a dedicated future detector that would look to be really good at the kilohertz regime to really study these neutron star equations of state and all these other things we've heard about, which could be very exciting. So we don't really need this slide, I think, by now, by Wednesday after lunch. But I did it for the sake of completion. And really the takeaway here is that when I'm talking to the non-numerical relativity community, it's nice to reassure people that just how much diversity we have. A lot of us work based off of the Einstein toolkit, but as Carlos just talked about, there's a lot of difference between the RIT code, which does use Einstein toolkit infrastructure to some degree, and the SPEC SXX collaboration. There's everything under the sun is different. So, and then there's a variation between all the groups between those two. So we have three main formulations. I didn't include Z4 on this slide, and I should have. We have several NR codes. We have a lot of different ways of approaching this problem, and we all agree with each other to the extent we can compare against today's data. It's tricky for us to compare things when we do precession or eccentricity. Precession, because it's hard to pinpoint what the spin values are that we're going to compare between groups at a certain time or frequency. Eccentricity, because that's even a hard thing to define since it's really a Newtonian definition. But nonetheless, we can do these comparisons and have done them. So it's a pretty solid state right now with current accuracy, how we all agree. So that's just a feel-good slide, I guess. Here's the future detectors, the pretty pictures for the future detectors. We have the current infrastructure of LIGO holding it the same length and just doing upgrades to the mirrors, to the laser, what have you, squeezed light, etc. And so we call that, they call that advanced LIGO or A+. So all that in Voyager could be happening, keeping with the current detectors that we have. And then if you look at sort of this bigger picture, you have the Einstein telescope in Europe, which has had a big positive thing because I think they got some kind of official status in the European Union. So there is underground 10-kilometer arm length in a triangle. So that's the upper left picture you're seeing. That's obviously an artist rendition. This thing is not funded to be built as of now. And then we have Cosmic Explorer, which is the US version of that. It's using the same technology that you would have in sort of the A++ or Voyager type of LIGO situation, but in really long arms, 40-kilometer arms. And so that's a picture that Matt Evans drew to invoke that image in your mind. So those are the two big ground-based detectors that, if funded, would really bring us into the future of gravitational wave astronomy. And of course, there's also the space-based mission LISA, which is led by the European Space Agency, with NASA as a junior partner. And that would be the picture on the right, which is the 2.5 million kilometer arms in a triangle design. So you have the double detector. And it's obviously, these are space satellites with a mass in the middle. It's a smaller mass than the mirrors we're used to looking at in LIGO. And it's orbiting the sun, traveling behind the Earth. So it's an incredible mission when you start to look at the details of the mission itself. And the discussion of the ground base, the first three, not LISA, is ongoing right now at the Dawn workshop. So that's a nice workshop if you guys want to check it out next year. And it looks at the future of gravitational wave detectors. So what are the demands it brings us? When you think about all these fascinating detectors that people are working so hard to design and attempting to get funded to start building them, I'm going to look at this in a super narrow numerical relativist viewpoint. In fact, I'm looking at it as a binary black hole numerical relativist, so it's an extremely narrow viewpoint, and ask the question, what are the demands it brings? I'm kind of lying because I did mention a few facts that aren't so narrow, but I didn't mean to be exhaustive. So the three demands that this has that I tend to think about is the different and broader frequency ranges, the potential for high signal-to-noise ratios, and multiple signals at the same time. So this big plot that you're looking at below is the typical plot we show of the characteristic strain, that delta L over L, and L is the length of the arm of the detector, versus the frequency in hertz. And you always see these noise curves that get drawn. And Carlos mentioned most of these, right? So you have on the left, at very, very low frequency, the pulsar timing array. I won't mention anything about it today. And then we have the LISA range at like the 10 to the -2. And then we start getting to the 100 to 1,000 hertz in the ground-based detectors today. And I put the little plot on above because this big plot hadn't shown the Cosmic Explorer and the Einstein telescope, so you could see how much more sensitive it should be than LIGO. So when we look at these plots, for the ground-based detectors, you have broadened out a little bit to lower frequency and higher frequency compared to, say, we pick LIGO or Virgo right now. And you've also got a lot more sensitivity. But you're looking at similar sources to what we have now, although the ground-based detectors, as they go to lower frequencies, will be very sensitive to black holes of the intermediate mass range. So things that are 1,000, 10 to the 5th solar masses will become extremely, those detectors are extremely sensitive to that. And as you move to LISA, you get your supermassive black holes, 10 to the 6th, finite black holes merging. You get a lot of sources there. And what happens is you get some potential for really high signal-to-noise ratios. So I'll just unpack this a little bit. It's a boring slide, no picture, sorry. So if you look at the broader or different, like LISA or PTA frequency range, we add potential sources. So we end up with our supermassive black hole binaries or intermediate mass ratio binaries. Now extreme mass ratio for LISA, where you have a really big black hole with something falling into it, where perturbation theory will reign supreme. And even things like galactic white dwarf binaries, which, I mean, I wouldn't be able to predict what their waveforms look like. They're pretty simple. What also happens, you get an increased length of signal and band. So you have that potential problem of, do you have enough orbits? Is post-Newtonian, we think of just the binary black holes, is post-Newtonian accurate enough as we come in over, as we get closer to merger? And when can a numerical relativity pick up? Can we do enough orbits to take over where post-Newtonian might start to lose its ability? And then, of course, I threw in observable universe because I think it's really cool, but it's not my specialty, so I can't really talk too much about it, but I find it very exciting, all the possible connections with cosmology. The second problem, the one I'm going to focus more on, is this high signal-to-noise ratio problem. I mean, it's not a problem, right? It's fabulous. That's what we want, because you're going to be able to see these signals beautifully, especially with something like LISA. because the supermassive black hole binaries are so large, they're just going to be potentially, a few of them could be 1,000 SNR. And considering LIGO right now, we're used to 33 being like the highest, this would be a big difference. It's a game changer for precision tests of general relativity. You know, I think maybe astronomers don't care if we're that accurate on parameters, but you can do amazing parameter estimation potentially, especially with things like the chart mass. But of course, it does increase the accuracy needed from the people who model the waveforms and do theory, right? So that's where the big need as we look to the future comes in. It increases the length of time for doing the computer to solve, even just to solve in numerical relativity, increases the length of time, so we need more accuracy, longer waveforms, different parameters. But also, if you're thinking about it as a data analysis person, trying to solve to find these events as you get in that data, it's also going to be very hard. And one of the reasons that's going to be harder, or a different challenge than we've seen so far, is that you can have multiple signals. You will have multiple signals at the same time. So we live in this world of, right now, LIGO Virgo, the first event, right, the famous GW 150914, was 0.2 seconds in band. So, you know, the likelihood of having multiple signals at the same time is small when the signals are that short and when you don't have such a sensitive detector. Of course, now you see, as LIGO and Virgo get better and better, the number of signals is going up tremendously now. We're at over 50. And it turns on again in the fourth observing run, where we should have just 100. But now in this world, you need to do something called the global fit, because you're going to have to assume that if you have a binary black hole merger that could take weeks to almost a year to merge in band, and it has a high signal to noise ratio, that at the same time, you're going to have potentially extreme mass ratio and spirals happening. Galactic binaries are always there that you have to remove. So you could have many sources happening at once, even multiple binary black hole sources happening, and you'll have to somehow fit for all those at the same time. So it changes, I think, in my opinion, it changes how well we have to model things, because if we leave something behind, it will detract what else we take out. So even though you would see this beautiful, mythical 1,000 SNR binary black hole signal, if you don't do that super well, you might be contaminating, and we don't get the best science out from the other signals. So that's what this is evoking. So you can imagine from that, if I've convinced you from that discussion, that you really want to have this indistinguishability. In other words, I'd always want every waveform that I fit in that beautiful global fit in the LISA error or the Cosmic Explorer error, I want the errors to be less than the noise. Then that's a large demand for some things. So people have been looking at this a little bit. In the 3G, so in the ground-based detectors, there was work done by Michael and Carl, where they were looking at how good the models would be for these future ground-based. They didn't talk about LISA, but they talked about the Cosmic Explorer and Einstein Telescope and A+. And, you know, they saw that they might need to, you know, really get their models to produce by 3 orders of magnitude to fully take advantage of the science in these extreme cases where we have really large signal-to-noise ratios. With then graduate student Deborah Ferguson, now she's a postdoc, we worked on a pretty simple example where we focused purely on numerical relativity errors and asked ourselves, just for truncation error, our inability to, you know, that we discretize the equations when we solve them, and that means they have truncation errors, we just looked for what happens when the SNR increases. And so that plot on the right is from that paper. It's the LISA only. We also looked in LIGO. So today's LIGO, we were fine. The SNRs aren't big enough for the numerical relativity errors to matter. You know, we can argue because if the parameter is not being fully covered, the other things can matter. But this was for the LISA, so we're thinking of a much larger SNR. I think the SNR for this was 600. And what this is, a Q equals 6. So one black hole is 6 times more massive than the other. The spin was about 0.2. And we gave it a little inclination to increase the role of the higher order modes. And you see that the black was a high resolution template or waveform, and the blue dotted was a low resolution. And if you remove those from the signal, you get left out a resolution residual in blue. And for fun, we also plotted what would happen if you took a 2-2 only template, so just the dominant mode, and not including all the higher modes, versus a template that had all the higher modes, not all of them, but most of the relevant ones that were in the black and the blue, and you would get this residual left. And you could imagine that mistakes you make like that of not having all the physics could also contaminate signals that are beneath this large binary black hole signal. So it's not exhaustive, but it was to feed the thinking about how important this could be. So to dive down into that a little bit more, because of this audience, I thought some people might be interested in it. You know, to understand how we thought about these errors more in this relatively simple case of just looking at truncation error only, are there other errors in numerical relativity? Most certainly. Carlos talked about a few of them, right? We have extrapolation to infinity. We are creating a strain we extract psi4, for example, the Weyl scalar. There's mesh refinement errors that are coming in. So there are other errors, and we're just picking out one of them. So the takeaway actually from this slide is that we don't actually have a really good measure in the community to assess accuracy. So the one here that I'm going to talk about, which is looking at the error in the waveform. So the waveform and then the error because you don't have the full solution, right? You have some discretized solution to the Einstein's equation. So that error, delta H, you could look at the overlap between delta H and itself and demand it be less than 1. It's a pretty strong criterion. So it could be that we could loosen this up a bit and still be quite good enough when it comes to high SNRs. We just don't know what that criteria looks like. We could look at maybe parameter estimation or something, but I just wanted to let people know that this is not, having the right measure to assess accuracy is not a solved problem. So what we did was we started with that condition, and then we wanted to find a measure in which would be directly related to that grid spacing. So if I look at my little grid on the right, my cartoon of the grid, that's just to tell you what is delta. So delta is just the grid spacing of the finest mesh that covers the black hole. So if you did 1 over delta, you'd be talking about the number of points across the black hole. And since this is a finite differencing code, unlike spectral codes, that all looks pretty uniform in grid spacing, even though there's mesh refinement. And so what you can do is, if you knew what the Richardson extrapolated waveform was, which would mean that you know exactly, you could predict what the full solution with no truncation errors was by extrapolating from your errors. If you knew what your convergence rate was and everything, you could predict the Richardson extrapolation waveform, and you would have the right solution to the equation. We don't quite do that, but we can predict the error. We can't predict that beautiful, perfect waveform because the solving of this stuff is messy. We have mesh refinement and other things that kind of ruin that beautiful convergent picture, but we are convergent, so we can find the error between our waveforms and at a finite resolution and the one at Richardson extrapolated. So we determine beta. We determine that, we find that waveform, knowing our convergence rate alpha, and then I'm telling you what beta is because you need it for the final equation that's in this little box. So beta is related to the derivatives of that waveform. And so we get an error, a match between 2 different resolutions, and then we can predict the error we would get if we did it to the Richardson extrapolation waveform. And at the end of the day, if you know alpha and you know beta, and you can calculate beta from that equation above, you can figure out the relationship between number of points across my black hole or your grid spacing and the signal to noise ratio of rho. So we liked this because it allowed us to study as rho increases, so that signal to noise ratio increases, what would the demands be placed on our grid resolution? So the plot on the left is for a current style detector, which is seeing black holes around 50 solar masses. That's the orange plot line. At signal to noise ratios around 33 or less, which is what we would see today. And you can see that we are using the grid spacing that would be appropriate for that to beat this indistinguishability criterion. So for today's detectors, we're pretty happy. So that wasn't a very smooth description, I apologize. If we look at future detectors, Cosmic Explorer and Einstein Toolkit are in the paper, but I grabbed Lisa because that's the extreme case. And you look at what sort of our And we don't have the most, this SXX code is more accurate, and we should throw on some of Carlos's plots up here as well to see where their resolution sits. But if I took one of ours, not working too hard, but still a decent waveform, and I did M over 400, that's that horizontal line, and you could see that once we start getting to SNRs that are really big, we're gonna not be able to, we would still have residual left over at the end of the day. So that's what we're trying to work against. And can we get to resolutions this good? Not with the code we're using. So, right now the big game is going to be how are we improving these codes to make sure that we can get to resolutions that are good enough so that we would be able to beat this indistinguishability condition. And those colors, the blue and the red, were just a few different waveforms to kind of give everyone a sense of how things change versus mass ratio and the inclination of the binary. So what are our challenges from my point of view? I think I focus on this faster, more efficient scaling of codes to achieve such many cycles and high mass ratios, because I'm not somebody who builds codes anymore. And so I find this to be, I'm very excited that many people in the community take up this challenge so that we're good at it as we prepare for these new detectors that will come in the 2030s. The accuracy requirements are being placed on it because we just don't want to leave any physics behind. I'd hate it to be that the errors that are dominating come from our side of the woods instead of the detector. One of our problems is we have to figure out how to set realistic accuracy requirements so we're not working harder than we have to and placing larger demands. And I think for me, and maybe Helvi and Luis are going to talk about this more when you think about going beyond general relativity. If I really do believe that we have to get general relativity really correct before we'll be able to find smoking guns of deviations of GR, unless those smoking guns are obvious, like a third polarization. So if it's going to be something subtle, and if it's going to be strong field, then we certainly don't want to have anything left in the tank that was actually classical general relativity that we hadn't solved well enough. I have this exploring thing there because, well, one, because I wanted to give a shout out that Irene's going to talk about machine learning later. More and more people are looking for alternate ways to solve things, exploring different types of parallelism. Spectre was looking at tasks, I don't know if they still are. Differencing schemes, can we be implicit, etc. So many ways we can go. Machine learning to do all sorts of things. So there's a wide open future for being more innovative in computing. I think it's easier to do it now that we have a solution to Einstein's equations, so it's not a shot in the dark. But it's an incredible amount of work. So I just applaud everyone who is moving in that direction. It's my challenges slide. We heard a lot of this in the lab from Carlos before lunch, right? So if we look at all the things we currently in the binary black hole world can do, we certainly can do non-spinning mass ratios less than 15. Carlos showed you one of a mass ratio up to 1 to 128. Beyond that, even that is not something people do regularly. We can do random spins. We can do precessing spins. It's just hard to compare with each other, and that phase space or that parameter space isn't fully fleshed out. We certainly can do them. What we don't have a lot of is highly unequal precessing. So we just have to build up more there. What we also don't have a lot of are eccentric. There's nothing really stopping us from doing that except that it's a little bit random how you define eccentricity. You saw some from Carlos for lunch. So we can do it, aren't that many in the bank. People are building models nonetheless for eccentric waveforms. We just need a lot more of them. And probably as a community, we need to have agreement on how we should define eccentricity so that the people who model or the data analysis community isn't confused. We can do tens of orbits. SXX collaboration has one that's beautiful, really long. And we're good at higher modes up to about maybe L equals 6 or 7, depending on which code you're using. But when we look at the future, we're going to need to have completely covered that parameter space such that the model could also then use our waveforms to fit to that complete parameter space. We need to be able to have this high accuracy, longer waveforms so that we can get all the physics out that's possible. And right now, there's been a lot of really interesting work, and I didn't put any papers down, and I should have, about better gauge conditions and extraction, because so far everybody's agreed. And that slide I had earlier, I was like, kumbaya, numerical relativity. We can use different formulations, different gauges. we all agree. Is that going to hold up as we go to this much more accurate situation? You know, we have to study that, and people are, and it's been very interesting. And I already talked about Helby and Luis's talk later in the week, but it's really exciting to think of what can we do for beyond GR as we move forward. So this slide, I just think it's fun. We're writing a white paper very slowly in the LISA waveform working groups. This is part of the LISA consortium. And as part of that white paper, so this is preliminary, it's not published, there is a collection of current and codes that are starting to be built. And this is the list I have right now. So if anyone in the audience has a code that I haven't included, you just email me and I'll populate this table. But I just think it's exciting to look at what's happening out there. I should put one that says whether or not it's complete or not. But for example, Spectre is being built, right? Spec's their current code. So if you look at this, we asked which ones are open source, which one have a waveform catalog right now. Some of those waveform catalogs are neutron star, which I'll have to take out for this paper because it's only concerning black holes, but for this group, it's interesting. What formulation do people use? Is there hydro? And does it have a beyond, or has it been used for beyond GR? So I just think it tells you just how exciting the space is. There's a lot happening, and a lot of people working on it. And it will all have citations, so you can go look at the code. This is what I meant. It's preliminary. It's not quite fleshed out. So like 2 minutes early or something, good for me. In summary, what's going on, right? So we're going to see gravitational wave detectors steadily improve. And I'm not 100% sure how we transition from where we are now to this glorious future in the ground-based space. I think they're going to try to always have gravitational wave detectors going, especially when you think about all the potential EM follow-up telescopes that could happen, missions. You don't want to be quiet in the gravitational wave band when all that stuff is happening. Hard to follow up if there's nothing there. So the detectors are going to continue improving, and that opens the door to discovery with both better sensitivity and better detection volume, because you can just get out further and further in our space. So this is going to increase the requirements on the waveforms on all fronts, post-Newtonian, numerical relativity, the people who model, etc. So I think we still have, even in just the binary black hole world, we still have an important role to play, and we're not done. We have to not only explore the parameter space, but improve the codes so that everything's faster and more efficient. And all this is happening sort of right now, even though it sounds like everything's pretty far in the future. So I think it's super exciting time to do this work. So if you're a student, well done, because I think you're going to have a lot of fun things to do. Thank you.